The
Okay,
next speaker is Aviral Srivastava, who will talk about non-Rascoe partitions. Please.
okay. So, good evening, good night, good morning to whosoever they're in the different time zones. And first of all, thanks to Melvin and the organizers for giving me opportunity to talk in this 24th edition of this combinatorial and additive number theory conference. So, as the title suggests, I will be speaking on non-Rascoe partitions and a rank parity function associated with Rogers-Ramanujan partitions. And this is the joint work with Professor Atul Dikshit and Gaurav Kumar. So, to begin with, some of the participants already defined the partitions, but yeah, let me define them again. So, a partition of a positive integer n is a non-increasing sequence of positive integers whose sum is n, and where each positive integer making up the partition is called a part of that partition. So for instance, there are 7 partitions of 5 and they are given in the example. And the function Pn denote the partition function which actually count the number of partitions of a number n. So as in the previous example, P5 should be 7. Now let me define a well-known object, Dyson's rank. So Dyson's rank of a partition is defined as the largest part minus the number of parts. And for example, if 4 plus 1 is the partition of 5, number of parts are 2, 4 is the largest part, so 4 minus 2 is 2, which is the rank of this partition of 5. And Dyson's rank played a very instrumental role in proving first two congruences of Ramanujan partition function. Now, let me go to the generating function. So, let Pn denote the partition function as defined in the last slide. Then the generating function is given by 1 over qq sub infinity, where uh, a q sub n notation is given below. So it is Q Pokemon notation. And so similarly, if you see the number of partitions into distinct parts, say where parts cannot repeat, say the partition of say 6, 1 plus 2 plus 3, parts are not repeating. So let PDN denote the number of partitions into distinct parts and PON denote the number of partitions into odd parts. So PON is basically where no even part can occur. Okay. So for instance, the partition of 6, that is 1 plus 2 plus 3, is not a valid partition because 2 is a even number. And say 1 plus 3, which is a partition of 4, is a valid partition because all parts are odd. And with these notations, the generating function of partitions into distinct parts are and partitions into odd parts are given respectively. So it is minus q sub infinity and 1 over q square sub infinity. Now, Euler did a very fundamental work, which is a widely known theorem in partitions, is Euler's theorem, and it says that number of partitions into distinct parts is exactly equals to number of partitions into odd parts. Now, we can actually rephrase the Euler's theorem. The rephrase is as follows. So the number of partitions of a positive integer into parts which differ by at least 1, that is basically distinct parts, is equals to the number of partitions of that integer into the parts which are congruent to plus minus 1 modulo 4, that is exactly the odd parts. Now what about the partitions in which parts differ by at least 2? Do we have a similar kind of theorem or similar kind of analog? We actually have. That is Rogers Ramanujan identity. So Rogers Ramanujan identity is a sum to product identity, and it is very well known. And now if you see left hand side of this identity, although I will not prove that, but left hand side of this identity, that is sum side, actually generate partitions, number of partitions such that the gap is at least 2. So left hand side generate all those partitions where gap is at least 2. And if you see right hand side, which is the product side, it actually generate all the partitions where parts that can appear are either modulo 1 modulo 5 or 4 modulo 5. So again, we can rephrase Rogers Ramanujan identity as follows. The number of partitions of a positive integer into parts differ by at least 2 equals to the number of partitions of that integer into the parts which are congruent to plus or minus 1 modulo 5. Okay. Now, since the left hand side of this Rogers Ramanujan identity is actually generate the partitions where part differ by at least 2, so we call such partitions where part differ by at least 2 as Rogers Ramanujan partitions, as I mentioned in my title. So these are Rogers Ramanujan partitions. So partitions which differ by at least 2 are Rogers Ramanujan partitions. Moving on, let me define another terminology, that is rank parity. So let P dash denote a subclass of set of all partitions P. Then rank parity function associated to P dash is the generating function of the excess number of partitions in P dash with even rank over those with odd rank. Let me recall, rank is largest part minus number of part of the partition. And if I again denote REN to be the number of partitions in P dash with even rank, and R sub ON denote the number of partitions in P dash with odd rank, then the rank parity function is nothing but the generating function of REN minus RON. Now, let's see some interesting generating functions. So if I take P dash to be the set of all partitions, then corresponding rank parity function is Ramanujan's third order Mach theta function. So if we are taking all the partitions itself, then the corresponding rank parity function turn out to be a third order Mach theta function. And Mach theta functions are basically weight half Mach modular forms, and Mach modular forms can be regarded as the holomorphic part of something called weak harmonic mass forms. So weak harmonic mass forms, if they have the holomorphic part of weak harmonic mass forms, if they have the weight half, then they are known as Mach theta functions. They are very well-known objects in the theory of modular forms. Now, if I move on to P dash, say, which is the set of all partitions with distinct parts. Now we are shifting our class from all partition to partition into distinct parts. Then the corresponding rank parity function is another famous function of Ramanujan, which is sigma function. And it also has some modular properties that I will describe in the next slide. And it also appears in sums of tails identity of Ramanujan, which was presented last day by Gaurav. Now, moving on, we have seen set of all partitions. We have seen the rank parity in case of the parts where parts differ by at least 1. Now what about the partitions where part differ by at least 2? Now the question is, what is rank parity function for Rogers Ramanujan partitions? Essentially the partitions where parts differ by at least 2. Before answering this, let's see why it could be an important object to study. So as I mentioned, the third order Mach theta function is an Mach modular form of weight half, and the sigma function, which was rank parity function for distinct parts, is actually a quantum modular form. So quantum modular form is kind of weakly a modular form where the modular difference of the modular transformation is not exactly 0, but nice continuous analytic behaving function. Also, sigma q has nice arithmetic property. If you see the Fourier expansion of sigma q, the coefficients are very nice, and some of these properties were proved by Andrews, Hickerson and Dyson in their paper, and they have associated the sigma q function with the arithmetic of q root 6 field. Now moving on, sigma q again naturally occurs in the sums of tails identity of Ramanujan, which is the identity given below. And there are many other rich properties of these rank parity functions. So it is obvious why not study the rank parity function associated with the partitions that differ by at least 2. And we did that. So here's our first theorem, which says let R m comma n to be the number of Rogers Ramanujan partitions of n with rank m. Then for absolute value of q is strictly less than 1, we have the following generating function. Now this is the generating function for number of Rogers Ramanujan partition of n with the rank m, where z take care of the rank variable. So now if I plug in z equals to -1 in the above result, then we will find the generating function of the excess number of Rogers Ramanujan partitions with odd rank over those with the even rank, and that turned out to be -2 plus sigma 2 function. We intentionally notated this with the sigma 2 being an analog of the sigma function of Ramanujan. Now, so this sigma 2 has this Q series expansion, and this is essentially the rank parity function associated with Rogers Ramanujan partitions. So when I plugging in z equals to -1, it automatically collects the even rank partitions and then the minus odd rank partitions, and we have this generating function. So this sigma 2q function we call as the rank parity function associated to the Rogers Ramanujan partitions. Okay, what are some of its properties? Before going to them, let me explain one other partition, that is Rascoe partition. So John Tyler Rascoe, also he is not a mathematics student. He worked in some ecology or some other area. So John Tyler Rascoe considered an interesting class of restrictive partitions, namely the partitions of a positive integer into distinct parts in which the number of parts itself is a part of that partition. And we call such partitions as Rascoe partitions. Let me give one example. So say you see the partitions of 11. 9 plus 2 is one such partition, because 2 is number of parts, 9 and 2. There are two parts of this partitions, and 2 itself is present as a part of this partition. So partitions where number of parts itself is the part of the partition. Okay. So for instance, another example, if we see 7 plus 3 plus 1, then there are 3 parts and 3 itself is a part of the partition. Okay. And if n denote the number of Rascoe partitions of n, then Rascoe gave the following generating function of n. Although Rascoe have not provided the proof, and there is only one account of this Rascoe partition which we found at OEIS sequence. So we were investigating some sequences we got, and we found out this is one of the thing that is of our interest. So this n denote the number of Rascoe partitions, and we have this generating function, and Rascoe have not proved it, but given this generating function. Now let me go to the non-Rascoe partitions. So non-Rascoe partitions immediately are those partitions where number of part is not a part of that partition. For example, there are exactly 9 non-Rascoe partitions of 11, and for example, say 8 plus 3 is a partition of 11. So 2 is number of parts in the partition, but 2 is not exactly a part of that partition, right? Now, if Bn denote the number of non-Rascoe partitions of n, then we have the following generating function, and which is immediate. Minus q sub infinity actually denote number of all distinct I mean the generating function of number of all distinct partitions of n. And if you see the other summation, it is essentially the generating function of Rascoe partitions. So it is very trivial that if I subtract all Rascoe partitions from set of all partitions into distinct parts, we will obviously get the non-Rascoe partitions. This is a trivial generating function. We will give one more generating function. Now moving on. Here is one of our main theorem. So while trying to find the rank parity, the idea was to investigate the rank parity function in the sense of modularity, congruences, and all those properties. And we found a very surprising connection, and it is our theorem 2. So connection is, if Bn denote the non-Rascoe partitions of n, then its generating function is nothing but minus q sub infinity times sigma 2 function, which was our rank generating function, rank parity function associated to Rogers Ramanujan partitions. So this sigma 2 and non-Rascoe partitions are very nicely connected to each other. Okay, and we have this generating function of Bn, and this third summation is one other equivalence that we have found, which is again the generating function of non-Rascoe partition. But the whole point of this is to see the partition or combinatorial interpretation of this sigma 2 function. Now, other theorem is kind of more in the Q series part. So this is a theorem of Adiga and Bhargava, and we utilize this to prove some of our previous theorems. Now, let me tell the Hecke-Rogers type representation of sigma 2. So say you have G function, and when I say the Hecke-Rogers representation of a function G, then it means the representation like this, where an comma j is a linear polynomial, bn comma j is a quadratic polynomial, and then there is the product 1 minus q raised to xn plus y. And it could be just a GQ function, or you can multiply some Q infinite product or something. But this kind of representation is called Hecke-Rogers type representation. Sigma Q function, which was the essential rank parity function in the case of distinct partitions, it has this kind of Hecke-Rogers expansion. Now, we also have one Hecke-Rogers expansion which looks like this. So sigma 2 function has this kind of representation. We have two representations. Although I have not mentioned, but Hecke-Rogers expansion again help us to go to modularity, congruences, or asymptotics, and there are lot of uses in the literature for Hecke-Rogers type. So we wanted to try, because sigma function itself has a Hecke-Rogers type expansion. Do sigma 2 have? But no, sigma 2 don't have a very clean Hecke-Rogers type expansion, because there is this q Pockhammer q sub j in the second summation. Now, there is this interesting identity which is kind of independent interest, but we have used this identity to prove connect one representation in theorem board with the other representation. And this identity, if you see the summands are equal except the powers. So here power is minus j raised times n plus l, and here minus j times n itself. And if we switch the power of q and the final and n and n plus l, the identity is very symmetric. So it is kind of independent identity we have in our paper. Now let me quickly give a combinatorial result which is the application of theorem 2 is as follows. Let pkjn be the number of partitions of n into distinct parts, with the exception that the smallest part, say j, is allowed to repeat exactly j number of times. So all other parts are distinct, but the smallest part j can repeat exactly j number of times. Then the excess number of such partitions with even a smallest part over those with odd smallest parts equals to number of non-Rascoe partitions of n itself. And this is this identity. Before I move on, may I know how much time do I have?
You have another 10 minutes.
10
Up to
minutes.
10
Okay,
minutes,
great.
yes.
So yeah, as I was saying, so PJN is the number of partitions of n into distinct parts, with the exception that smallest part, say j, can repeat exactly j many times. Then we have this theorem that Bn, that is number of non-Rascoe partitions, can be represented in terms of this partition class PJN. Now, to give you an example, as I mentioned in my early slides, there are exactly 9 non-Rascoe partitions of 11. So that is B11 equals to 9. To demonstrate the last theorem, P011 is that there is no smallest part. So we are just counting the distinct parts. So there are 12 distinct parts. Now P111 is, we have one smallest part which is 1 and it can repeat just one time. So we have 5 such partitions. And P2, that is 2 is the smallest part and 2 can repeat 2 times. And only admissible partitions are these 7 plus 2 plus 2 and 4 plus 3 plus 2 plus 2. And use so last theorem, as the last theorem says, if you sum these you will get 9, which is actually B11. So other part is the congruence for Vn. So we have the following congruence for Vn. So it is more or less about the parity. So the number of non-Rascoe partitions of n is odd if and only if n is of the kind m times 5m plus 1 over 2. And this, in this, to prove this result, you require our theorem 2. Again, this is application of theorem 2 and Jacobi triple product identity and Rogers Ramanujan identity. So we utilize this to obtain this congruence. Now we have an important conjecture. So conjecture is that Bn denote the number of non-Rascoe partitions of an integer n. And for any integer k greater than or equals to 1 and k being not a multiple of 29, k should not be a multiple of 29, then we have the following congruence. B of 29k plus 21 is congruent to 0 modulo 4. And k here should not be a multiple of 29. Although after our paper, if k is a multiple of 29, we will have some other congruence. So we have refined this conjecture a bit, but I have not mentioned here. So if k is a multiple of 29, we will have a little shifted congruence. So, but for time being, this is a congruence. And we verified this congruence for say 5 lakh values of n, and we are very surprised how these numbers are appearing. This 29k plus 21, how all of a sudden can appear. It may have some connection with say modular forms, or maybe I talked to some people and they say there could be connection with the finite extensions of Q, or something like this. Now, if we assume the theorem 6 and the conjecture above, then it will imply that the Diophantine equation 29k plus 21 equals to m times 5m plus 1 over 2 has no integer solution if k is not a multiple of 29. Although it is not a big deal of a Diophantine equation, one can elementarily prove this by hand. But this is just a small implication if the conjecture holds true and this theorem 6 holds true. Oh, wait, sorry, it's not a theorem 6, it should be the theorem 7. So if this theorem 7 and this conjecture holds true, then we have this remark. So I'm sorry, this should be the theorem 7. Now, I can give a proof of my theorem 1, which was the generating function of our rank parity function. So just let me give you the proof. So, okay, before just proving it, let me show the theorem to recall the statement. So this was our theorem 1, and I'm going to give the proof for this. Okay. Yeah. So proof follows now. So let n be the number of parts and k be the largest part of the Rogers-Ramanujan partition. That is partition where parts differ by at least 2. Okay. So if the k be the largest part of such a partition, and since the difference of any two consecutive parts is at least 2, so we can separate 1, 3, 5 and so on dots from this partition diagram. So we can separate exactly 2j minus 1 nodes from the jth part of the partition, and which will contribute to q raised to n square factor. Okay. And now if you see the remaining nodes of this partition, then we can generate them by using 1 upon z q sub n, and where the dotted region will contribute to the power k minus 2n minus 1 for this z. And to see that, you see this partition which is not covered in the boundary. Okay. So if we take these nodes and we do the conjugation, if you see these nodes and do the conjugation, then this largest part. This largest part will become number of parts of this partition. And if you see the number of parts of the conjugate partition, then it will contribute to the largest part of the remaining partition. And if you see the largest part, then suppose you have n parts, then then there are 2n minus 1 nodes that are under the boundary. And since your k is the largest part, so remaining part should be k minus 2n minus 1, which is essentially largest part of this partition and essentially the number of parts of the conjugate partition. So if you open this 1 over zq sub n, then it will generate number of partitions where largest part is at least at most n, and z will, the power of z is k minus 2n minus 1. Now since the power is k minus 2n minus 1 and rank is defined as the largest part minus number of parts, that is k minus n, right, in this case. So we need to multiply this extra factor z raised to n minus 1, so that the exactly z power is k minus n. And hence multiplying everything together, you have q raised to n square upon zq sub n, and then you are multiplying the extra factor z raised to n minus 1, so that z actually count the rank, and then multiplying all this together, it completes the proof. And of course we need to sum over all such n's, that is the largest I mean sum over all number of parts. So we are summing over n from 0 to infinity, and this is the generating function of the rank generating function for the rank parity function. Now moving on, I think I have 2 or 3 minutes left, so let me give you the concluding remarks.
1 minute.
1 minute. Okay, so let me finish it quickly. So in this work we have also generalized all the results with the parameter L, and the number of non-Rascoe partitions are studied in detail in our paper, and AN and its generalization also warrant a serious study if some of you could be interested. Also the modularity of sigma q should be investigated, and we ourselves are investigating the modularity of sigma q, and here are a few references. Thank you.
Thank you very much for your talk. Is there any question for our speaker? If not, I thank Aviral again. We have a half-hour break, and we reconvene at 1 o'clock New York time. Thank you all.